Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. RCDs. Right. Going to do a video now on types of RCD. Okay, because there's been a rewrite of the regulations, and it seems to be a hot debate going on at the moment. So this video is going to be talking about the different types of RCD, the regulation that's been introduced, and it's also going to kind of answer this question that I've written there, really. Why are AC RCDs still in the regulations? That's really what I want to talk about really here. So let's just cover this regulation. So the regulation is here. So this is the rewrite. Section 531 has been rewritten, and they've introduced different types of RCD. Now, these RCD types have always been there. A, B, all of them. They've never been written in the regs book. And towards the end, I'll talk about, how we're supposed to have done this prior to the 18th edition, but now they are in the 18th edition. Now, they're not all there. They've given 4. There are other types as well, but it gives us that that understanding there is a type to choose from, should we have not considered this before. I kind of want to take a spin on this regulation now, and whilst I understand why the regulation's been introduced to obviously help with this, I'm frustrated with this bit. The little bit here that says, for general purposes, the Type AC may still be used. I don't understand what general purpose actually means. Does general purpose mean RCDs for the purpose of additional protection? Does general purpose means RCDs for showers, for socket outlets, for whatever? It's just, it's a very, very uncommitted word to use, and that's going to create an opinion that this is the starting RCD, and only if it's a specialist scenario do we need to deviate from a general purpose. And I guess in the minor regulations it does do that in section 722. It'll start to talk about different types of RCDs, A and B, for electric vehicle charging points. In medical locations it will say you must not use Type AC, it must be Type A or whatever. And so the special installations and locations do help us with this, but we need to be more familiar with why AC type RCDs are not suitable. Okay, so is there a problem with AC type RCDs? Yes. A Type AC RCD, which is your off-the-shelf RCD probably still, it only operates on alternating residual current. This means obviously that if the residual current in an earth fault is primarily from a inductive or a capacitive load or a resistive load, then it's going to be alternating current that is leaking. Fine. But if this equipment has any kind of DC component that could obviously provide some level of leakage to earth, whether it be again photovoltaics, or whether it be power supplies, computers, washing machines, whatever, we need to identify that kind of leakage current being direct, being straight, and not obviously of a rising and collapsing alternating current, can become a problem for AC type RCDs. So much that they may fail to actually identify the leakage current, or they may actually really, really limit the sensitivity of the AC type RCDs. So, what can cause an alternating residual current? Okay, so we've had AC type RCDs for years and years and years and years. Tungsten, halogen lighting, ovens, showers, resistive, inductive, capacitive loads, all of this equipment that is linear, non-linear, that's absolutely fine. As long as the leakage current is alternating, then there's not potentially going to be much of a problem. The issue is today, though, with advancements in construction of electrical equipment, we are really, really experimenting and testing and trying out using electronics in a huge variety of our equipment construction. LED drivers and lighting, inverters, power supplies, solar, electric vehicle, washing machines even may use DC motors. So you're going to have rectification there. USB charging sockets. There's a rectifier in there that could fail. So we're using electronics to a heavy amount now. All of these things can offer failure, and if they offer failure from the DC side, it will be a direct current residual current. It will be a DC residual current, which AC type RCDs are not manufactured to see, and that creates the problem. So, manufacturers have been providing guidance and information on this. They've been doing it for years, but it's a case of electricians need to understand the true nature of the potential leakage currents and where they can come from. And that's obviously where the regs is going to offer some assistance now, but we should really have had more assistance before now. So some examples manufacturers will provide with this table here. So the typical type we're talking about now is the AC type, and it is just alternating residual current. That's all it's manufactured to identify, and it has a different operating principle to achieve that. A type, which is what we are now considering should be the general type really, also operates on alternating current, but identifies pulsating DC, so DC current up to 6 milliamp, which is a fairly good representation of a quantitative value of appliances in the home, for example. If we're going to push higher than that with a higher potential amount of leakage, we'll go to the F. Varying frequencies, we may go to the B, but naturally the more we go up, they are going to introduce more technologies. They're going to be able to achieve more magic tricks, so they're going to be a lot more expensive, hundreds of pounds for some of these types. But we are stressing that the AC type needs to be considered as to if it's any use anymore. Is it any use? So you'll also see, just to kind of help, if you do look at the information that the manufacturer will give, you'll also see them give you an example of the hysteresis loop, showing you how a typical AC or type ARCD would identify alternating current loops, but when they have a DC, there is an issue. I just want to quickly run through what the hysteresis loop is, should you be unfamiliar with that. Okay, so it's all about, obviously, magnetism. If you remember doing this back at college, level 3, science and principles, you probably covered the hysteresis loop back then, where we consider hysteresis losses. It's the same principle that we're looking at here, and that's why the manufacturers use hysteresis as an example as to how these RCDs and how these AC RCDs can be a problem if we have any DC intervening. So with a hysteresis loop, let's start at the beginning. We've got here an axis, a horizontal axis and a vertical axis, and let's just take this away to the bare point there. So the magnetic field strength and the flux density on the vertical. So here we have a point of 0. So right now the magnetic item is demagnetized. There's been no current applied to it, positive or negative, and it has no stored flux density. Now let's apply some current from the point of 0 up to a positive half cycle. So if you think about how the manufacturers present this, this is the same point of 0 to start with, but then there's this alternating residual current. This is the excitation by alternating residual current. So this is the residual current that's there. And as from a point of 0, it climbs to a positive peak of the half cycle. It goes from a 0 point to a peak point, or a point of saturation. Okay. This is the point, and saturation point is where it's going to stop gaining any more magnetic strength. Okay, it's saturated, which means it cannot become any more magnetized than it already is. In other words, we've applied the power to a point. That's the point of saturation. It's then obviously as the field, which is still in the positive but collapses down to 0, so it's going from its peak down to 0, that's going to apply less here. So what's going to happen from that point of saturation is the strength is going to fall as it returns to 0, but it doesn't fall all the way down to 0 because anything that has an initial point of 0, when it actually achieves this level of magnetic field strength, it doesn't lose it fully. When you collapse that current, it holds a charge, and that's illustrated here at a point we call a remanence. Okay, so you'll see here that when we actually start to go from the positive peak down to the 0, the field that's actually there, the charge within that, hasn't actually fallen to 0 with it. It's fallen some way down, but it's maintaining that slight level of charge. I could go into the whole the whole physics side of this, but it would be a little bit off topic, okay, with no poles and things. But do let me know if you want me to cover that. It's not really essential to understand this point. So we've got the starting from 0, we go to a positive peak, and it falls back to 0, and it's holding a level of charge. So we now need to have some charge carrying into the negative peak to pull that charge down to 0, but it's obviously going to be in the negative side, and as that carries on to a negative peak, we end up another saturation point. So we started at a 0 point of charge to a positive peak on the positive cycle, and we've then gone all the way to the opposite negative peak on the negative half cycle, and there are 2 saturation points. There are 2 points of peak currents. In this case, we're talking about, again, residual current. So here's an alternating residual current peak and an alternating residual current negative peak. It's AC, so it has positive and negative peak of residual current. That creates this hysteresis curve here. And then we get to this other saturation point, then it's going to start climbing back up to 0, where it joins the... Basically, it's going to repeat this. Now, it doesn't go back to 0, because when it goes from a negative charge peak, as it goes back to a 0 level of strength, it's not going to offload all of that magnetic field. It's going to stop here, just like it did on the positive cycle. It stopped halfway downish. Here on the negative cycle, it's going to stop about halfway upish. And then when you apply it to the positive peak, it then creates the full loop, which looks like this. And this is called a complete cycle, or the hysteresis loop. Now, when you go back then to how the manufacturer illustrates that, you can see that illustration there. Now, it's a narrower hysteresis loop, so this is obviously a much thinner field. Obviously, larger solid magnets have thicker hysteresis loops, but obviously much thinner film. Again, this is going to be a toric coil. Will have a very thin hysteresis loop. This is the hysteresis loop of a Type A RCD, I believe, because the ACs have a slight kink at the top. Okay. In fact, I've got a slide with that just there. There we go. So here's an AC type hysteresis loop, and here's the A type hysteresis loop. And the thing to note, if you remember this remanence, which is the point where it no longer actually, it still holds a charge, but it's idle. It actually, on the AC type, is much larger. So when you've actually powered that up from 0 all the way up to its peak, and then you start to collapse back down to the 0. So it's gone from a 0 current to a positive peak down. So that's basically one cycle of the AC waveform. It's holding a lot more charge than if it was an A-type RCD. Okay, the remanence falls a lot lower with the A-type than the AC type. Okay, principle of the 2 different RCDs. But they both operate in these cases, though, with alternating current. So you have an alternating current there, and this is illustrated here. There's naturally going to be, after one there, there'll be a negative peak, which is illustrated with the tail of the hysteresis loop there, that half. So the manufacturers have illustrated this principle here. So this is one example. I think this was Eaton's example. So you've got the alternating residual current going down. There's the alternating residual current. And then this hysteresis loop is created. And then this loop creates a field there, and it's the voltage in this that will then be induced into the sensitive coil in the RCD, which then be rated to its setting. So we need to have this here is where we actually get a resulting magnetic flow that is actuated. It says that they're actuated. Okay, that will create the induced voltage into the actual sensitive coil. Now, if we jump over to this other side, then this other hysteresis loop, which I'm slightly blocking, you'll see that the whole thing has shifted along the h-axis by a representation of the DC residual current. And that DC residual current shifts it along because that's a constant current. That's not an alternating current. So wherever it starts from, it's going to be a new starting point. And this is what we would call, this is where we would say that this because it's a DC current, you'll notice that this is all to the right of the axis. Okay, so this whole thing is to the right of the axis here, not to the left and the right, equally like this hysteresis loop. This is to the right more. This is where we say it has a bias. The presence of the DC residual current results in there being a bias to one side of the positives or negative AC waveform. And because it has that bias, we require, when we have this DC current, a device that will actually monitor, we're considering that bias, and that's what the pulsating DC is like, where it's monitoring one side of the waveform. So how's the hysteresis loop affected with this kick by the DC? Well, it still starts at a 0 point, much like the other one. But as you'll notice, because of this, let's say that this is up to 6 milliamp shift, because that's the maximum for an A type anyway. Because of that shift, then we apply the AC residual current onto that. We have this much longer stretch to that point, and that results in a much narrower magnetic flow actuated by an alternating current here and direct current. So here, the actual resulting magnetic flow there, okay, it's much thinner because the DC has pushed it further away. The conclusion is it's much less likely for an alternating current, residual current, or an alternating residual current to be detected in that small window when a direct current is also in place. So it'll work on two principles. It'll work on the alternating current principle, similar to this method, when there's no DC current leakage. That's fine because it wouldn't have shifted over. But once it has been shifted over, it's going to obviously work through another means that will not stress or particularly work on alternating currents. So this is an example of why we have an issue with AC RCDs. AC RCDs purely work on this principle here, and if we introduce DC residual current into our equipment that actually is only protected by an AC type RCD, we're going to have this scenario where it's been shifted over with a much thinner window. This is why it might become blind, in the words of the manufacturers, or it might become very, very less sensitive or very unreliable, because it's going to be obviously the likelihood of catching the voltage induced of the voltage created here induced into that coil. It's very, very unlikely. Similarly, another thing that is a problem with alternating current RCDs, AC type RCDs, is if the equipment obviously offers a varying frequency. If we have increased frequencies, then this frequency of the residual current will be so rapid that it won't actually capture. It will rise and collapse quicker than the actual voltage can be induced into the coil, into the actual toroid coil. And so by the time that the device actually starts to identify the voltage that's created by the residual alternating current, its frequency is so fast that it's actually risen and then collapsed to the negative peak so quickly that the thing hasn't been able to respond in the time frame. So quicker, higher frequencies, DC currents, both are problematic to AC type RCDs. Another manufacturer bit of information. This is the Siemens one. Is here. So this illustrates these two. This one and this one are just illustrating the same here. They've taken the actual outside the hysteresis loop out of these illustrations for completeness. Okay, but the actual main line there, this main line, is still in there. And that's here. So here we've got the alternating residual currents, positive, negative. Okay, and then the tripping signal that's generated by the alternating current here. Okay, it's good. Good alternating current equals good alternating signal. Easy to achieve. But if we have a DC residual current, it shifts over here. Okay, so this one is the modulation with the AC residual current. And this 3 is the superimposition of the DC residual current, I delta DC, with the AC. So there's been that shift, and then there's AC. And that's resulting in this thin window here. Tripping signal on superimposition of DC residual current with AC residual current, total residual current. So it's all the way over there. Okay, and that is a tiny window that's not going to achieve sufficient voltage to actually be imposed onto the or for an EMF to occur to be imposed onto the toroid coil. It's not good. Not good. Okay. That's why the manufacturers are showing that if you do some reading on these RCDs and you see these, that's why they're illustrating them. Okay, it's all back down to the understanding on magnetism and understanding about the, think of them as windows of opportunity for the actual actuating current or the voltage to be opportunistic, to then be induced into the toroid coil. And with an AC RCD being subjected to an alternating residual current, fine. But if we subject the DC to it, it's such a smaller window that it's unlikely to be of substantial enough voltage to create the EMF to be induced into the toroid coil. So the answer is, do not rely on alternating current RCDs to protect against any current that is direct. It's going to create this problem. Okay. So the next question really is, why is this now a thing? Why is this now something that's being discussed heavily online and all that? Why wasn't this a thing before? Well, it has been covered before, but very badly. This is a rewrite of a regulation in BS 7601. Previous to this, it wasn't mentioned. There was no mention of that, different types. It was covered in a couple of different areas from a do your own research perspective. You know, let's remember that the one regulations isn't what we need to work to, it's what we need to work from. And that is very important. Where we would have approached it before, and we have picked up on this before, is using the external influences in chapter in Appendix 5. Appendix 5 gives us external influence category, one of them being DC current and an AC network. AM7, and that gives us a regulation 321.10.1.7. Great. You go to that, and then you realise there's nothing there. This is something that's been in there for a number of years. Again, I've said before, I've said it online, and I've said it in videos, and I'll say everywhere. The wiring regulations are not perfect. They're far from perfect. This is an example where there's just missing information or it doesn't work, and we now need to find the extra support. Okay, and that's what they've done with this rewrite, I guess, but it's raised a lot of questions. Okay, so to conclude, what has the industry done? Now I'll just cut while I get a couple of things to play. When we think about, you know, what does it mean to say? What does it mean to say general use? You know, ACRCD is okay for general use. This is the operating manual for a washing machine, Siemens washing machine, and it's got in there, one of the first things it says is this is intended use. This appliance is intended for private domestic use only. So this is something that any homeowner could go and buy and put in, and their fixed electrical installation should, in theory, be ready for them to buy this equipment. But it says in here, remember it's a domestic only item, if using a residual circuit breaker, use only the ones that bear the following mark. And this is the mark for an A-type RCD. In other words, do not use an AC-type RCD with this washing machine. So again, I go back to the title of this video. Why do we still have AC-type RCDs if the construction of electrical equipment is going down the avenue of using electronics to this point where AC RCDs are going to be unreliable and potentially dangerous? You know, we've got to try to improve our understanding on these different currents, these different residual currents, AC or DC, how they behave, what the differences are, and make sure that we select protected devices that are suitable for the life of the installation for the users of the installation. Now, AC RCDs may have a place where, I don't know, a shower circuit, unless electronics are involved with that, maybe. Lighting, you could have electronic lighting switches, dimmer racks, LEDs, drivers, probably not. Socket outlet circuits, you could have a wash machine like this one. You could have USB sockets installed, again. So there are many more arguments against AC RCDs than in favour of now. And it's something that, you know, we're all becoming more and more aware of. And it's a case of what we're going to do with this information and move forward. Okay, so you all know this place. Some electricians use this because it's just easier, more practicable. So you go here, you go for an RCD, and what you end up with is AC, 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 AC. They're all AC type RCDs. This obviously is a contributor towards the problem. We've just not had the ACRs, the A type, the B type, more freely accessible in the industry. They're very expensive. We've not had suppliers support us with our requirements to obviously select these devices. We are now seeing, as seen in another video from GSH Electrical, where they went to a Lex exhibition, we're now seeing the likes of Hager have created an 18th edition consumer unit, and they're putting in 100 amp RCDs A-type as standard, mainly from a common sense opinion. 100 amp being a rated current of an RCD to accommodate the current being pulled through. A-type being a sensible decision with regards to this problem. How we decide what is or is not a general purpose. If we go with an A-type as a starting point, as I suggested towards the beginning of this video, we have kind of, unless there's going to be more than 6 milliamp of DC residual current, you know, it's a lot better than an alternating current RCD. An AC type is just, you know, it's a better idea. So yeah, Hager have taken a step forward with that. Now this, I'm just going to play a couple of seconds now. Electrium, who own obviously a variety of the manufacturers, YLX and Siemens and a few others. They did a podcast, and again, they'll admit that it's flippant, but this is their response to this kind of question here.
And the regs don't say you've got to use a Type A either. They say that you can use the appropriate type. You should always use the appropriate type. And you know, rating of devices, choosing the appropriate rating, is somebody trying to say that that's new? Really? What, have we been choosing the right MCBs and other fuses and the like purely by luck? I'm being flippant, I know, yeah, but yeah. You know, choosing the right device that's not new to the 18th edition.
I mean,
right. So there's going to be no obviously recognition that manufacturers haven't offered support, haven't offered opportunity to be provided with more information. To be fair, the information has always been available. It's one of those things where many electricians just don't choose to dissect all of the manufacturer's technical jargon to fully understand the information there. And manufacturers obviously haven't offered the industry bodies as well. All the industry bodies and the voluntary bodies haven't offered this this information more readily until all of a sudden it's a regulation and everything has to take it on board. It's frustrating. It is very frustrating. We've got some. I'm going to show a clip in a second, and we've got some motions going on in the E5 group, and a couple of guys there have, they've worked hard on creating a good video. But this is something. I mean, the founder of E5, Paul Meehan, this is something that he's had on his radar for years and years and years, because he's in the rail industry, and things like things like electromagnetic fields being impacted impacting RCDs effectiveness is something that's been on his radar, and it's like he's been proactively working with for years. So this kind of thing isn't news to him at all, but the frustrations are there. So he's working on a video now with a couple of guys through E5. I'll show a clip of some of the content in a minute, but I do recommend that you go to that, where he'll actually talk more from a practical application about why these RCDs aren't behaving as they should when they're AC type in an environment subjected to DC residual currents, and more about the testing methods and the solutions that we can have. All right, I'll put a clip on as we leave this video, and I'll catch you in the next one. Cheers.
17, 18, and with time and wear, these will also change the characteristics of the device. So that's fine. So you've now tested it, you've certified it, jobs are good. And 6 months later, husband's received a shock. You've got to go back and you're thinking, well, what have I done wrong? First thing you'll do is you get your tester out and say, well, the RCD works, not a problem at all. So again, you'll do your RCD test, you obviously make sure power's on, you go half times and it won't trip, and you think, yeah, fine, there's no problem here. You'll go to 1 time, and what you'll also do then, you'll do 1 time and you'll make sure it trips, because jobs are good and it should trip out within 300 milliseconds. Oh no, there you go, it's not tripped out. What's happened there? Well, what I've actually done is I've just injected 250 milliamps of DC current. Now I don't know that, because I've just done my 1 times test, so I'm thinking, well, this is a mystery. How do I solve the mystery? I know what I'll do. There's a problem with the RCD. I'll push the trip button. That's what I'll do. So I'll push the trip button. No, it's not working. Bugger. So okay, so the trip button does not work. It's saturated with DC. So I've got a problem. So I'll tell you what I'll do. I'll do a ramp test to see if I can unseize it. Maybe there's something I'm not aware of. I'll do a ramp test and I'll see what test, and I'll see what test, and I'll see what test, and I'll see what test.